We're continuing with section 15.4, triple integrals and cylindrical and spherical coordinates. So let's remember the change of variable formula for triple integral look like this. If you had a triple integral over solid R with a volume element xyz, then you would take the triple integral on the pre-image of R, which is where the transformation of S gives you R of F. Instead of xyz, you would have x of u v w, y u v w, and z of u v w, which is the g of u v w. And then you will have the absolute value of the Jacobian and then the volume element and basically in the UVW coordinates. Now, if you're doing cylindrical or spherical, you have to find this Jacobian over here. And usually finding that Jacobian is for cylindrical is not very complicated, but still time consuming. For spherical, it's kind of it's very calculative intensive, so you don't want to compute it every time. You want to kind of memorize this. And so when you can compute Jacobian of this one is for cylindrical. Remember, derivative of first one with respect to r, then first one with respect to theta, first one with respect to z, which gives you 0. Then second one with respect to r, second one with respect to theta, second one with respect to z, third one with respect to r, theta, and z. And then you find the determinant the same way we found the determinant when we were doing cross products. That's using the first row to expand as very convenient way of doing this. And then when you find a determinant, you end up with r, which this is familiar. This also happened in polar. And there are so many similarities between cylindrical and polar that explains it better. Now you want to find the Jacobian of the spherical. So this one is, the second one is spherical. So for spherical, let's erase this part. So for spherical, you have x is this, y is this, z is this. So x with respect to theta will give you this. X with respect to rho gives you that. Theta gives you this. Phi gives you that. Again. Oh, I'm sorry. It says rho, phi, theta. So this one is with respect to phi. This one is with respect to theta. And here, y respect to rho, then y respect to phi, then y respect to theta, then z respect to rho, z respect to phi, z respect to theta. And then when you calculate it using the determinant, you end up with rho squared sine phi. So memorizing that usually doesn't create a lot of extra work, but I think people get confused with that one. I say still memorize this one. Rho squared sine phi is the Jacobian that you need for a spherical coordinate, and if you don't have it, it's not going to work very well for you. Now, let's see. Triple integrals and cylindrical coordinates look like. Now, if I simplify the way I did it with polar coordinate, is that you have an integral in form of xyz plane, xyz three-dimensional space. Then you want to take that back to r, theta, z coordinates. And so here you know that you have to switch x and y and z to whatever they are, basically do the conversion in cylindrical coordinates. So that's part of the job. And then you remember the Jacobian, and then your volume element is going to be dr, d theta, dz, basically. The order of these things can be different. It's just these are for you to take short notes for memorization rather than be accurate mathematical notation. So mathematical notation is not, I have to have dA over here because I don't know the order, but this way you remember it a little easier. Now, triple integral and spherical coordinates. So you again have that in the XYZ coordinates, you have a triple integral. What you do the spherical coordinate conversions for f, and then for dx, dy, dz, you write rho squared sine of phi times d rho d phi d theta in whatever order. I don't know what order that is, so don't forget the Jacobian and memorize that part. And so in short, you replace dx, dy, dz by r dr d theta dz, or rho squared sine phi d rho d phi d theta for the two other coordinates that we have. So example, so we said inside is still dz, then dr is going to run from 0 to 1, d theta is going to run from 0 to 2 pi, and so on and so forth. And then you take the integral from here. Again, this is Jacobian for cylindrical. And do not forget that Jacobian. So you set it up and then you solve. And so it comes down when you're solving over here, the inside would be z r to the third and z 1 minus r squared to 4, and then you plug it in and you solve, and this is what you're getting, and you integrate again, and that's the final answer. Now I click her B. Convert the following integral to cylindrical coordinates, and the integral is from negative 5 to 5, from 0 to 3, and from a negative square root of 25 minus x squared to a positive square root of 25 minus x squared, x dy dz dx. And pause and come back. Okay, now let's try to answer the question. What I see is that here y is between negative square root of 25 minus x squared and positive and square root of 25 minus x squared. It's minus x squared. And then x is between negative 5 and 5. So x, y, negative 5, 5, and this is the circle that goes around it. So basically what you see on the bottom, the xy plane, is going to be a circle. So it's a cylindrical coordinate, and then z runs from 0 to 2. So if I draw this, I have this and 5, and it goes and it stops, and I have to erase this part. And z is going to be the maximum, z is 3. And so setting this up, I see the bounds. R should be between 0 and 5. Theta is between 0 and 2 pi. And then what else? Z is between what? 0 and 3. So whichever matches that, and x goes back to r cosine theta, and then I have to multiply it by r to get to get a Jacobian multiplied together. So this one's out of questions. That's one thing. It should be r squared cosine theta. And then I have to have theta run from 0 to 2 pi. This one and this one have 0 run from 0 to pi. This one z goes from 0 to 2 to 5, so that's not correct. And this was not correct for that, so that is the answer.